So after these videos of conceptually understanding forces and being able to identify forces and draw free body diagrams, I want to make this video about how to approach problems where you're going to solve numerically, and then I'll make some videos that cover some examples as well. So a couple of things first. All of our problems that we are going to be talking about are going to have us looking at what we call inertial reference frames. An inertial reference frame is one in which the observer is not accelerating. It's a non-accelerating reference frame. Now, that may sound a little weird, but if we were, say, in a car and we're driving, and yes, my cars are terrible. So we're driving along and someone slams on the brakes. Slamming on the brakes would create an acceleration which would cause us to slow down really fast. Well, to us in the car, we would feel jerked forward. So jerked, not because there's an actual force physically jerking us forward, but because of Newton's first law. If you remember, Newton's first law, for every object that is moving, its motion is going to continue with a constant velocity unless there's a net force acting on it. So our bodies in the car, we've been driving down the road, so our body, the inertia that we have, wants to keep going. And I know it's not really wants, but Newton's first law, our bodies are going to continue forward. But the acceleration of the car, at some point we catch up to the car, and the seat belts keep us and force us to move with that same acceleration. So sometimes when we talk about what we feel, the feeling of being jerked around in the car, that makes us want to include a force as part of our analysis, which does not actually exist. So this is what we mean by inertial reference frames. A car, you suddenly step on the brakes, you slow down really fast. That is what's called a non-inertial reference frame. The car itself is accelerating. And so to try to make sense of what we feel, we can't use Newton's laws in that case. So just in general, this concept of inertial reference frames, as we analyze problems, we are always going to be an outside observer. Someone stationary, someone not accelerating. We'll just pretend that we're standing on the sidelines watching these things happen. Whatever, the car slowing down really fast, an elevator moving up and down, whatever the situation may be. So, outside observer is what we're looking at. When it comes to actually relating force to motion, that's going to be Newton's second law, where the acceleration is equal to the net force over mass. Objects accelerate because of the net force acting on them. Whether we write it and leave it as A is equal to net force over mass, or say the net force equals mass times acceleration, either way is totally fine. in the process of solving a problem, we will always draw a free body diagram, meaning account for all the forces acting on the object in the time period we are interested in. Label those forces. So force vectors that are labeled so we know which forces we are accounting for. Once we feel comfortable that we have all the forces, then we're going to write out the equation representing Newton's second law, whichever way we want to write it. Now, as we do this, as you walk through the samples I'm going to show you, we're going to always write these out symbolically, meaning no numbers at first. So everything in terms of letters. Part of the reason for that is just the practice and getting used to communicating our work. But another part of it is sometimes when we're new at solving problems involving forces, we get a little panicked if there's some information we think we need. But if we set the problem up symbolically, we will see that we actually don't end up needing it. So I'll show some examples of that as well. So again, write out equations symbolically, and then we'll start doing substitution, putting things together, and working through the problems. So as a side note, mentioned before, the force of gravity, the strength of the force of gravity depends upon the mass of the object and then the acceleration of gravity on the Earth, since our problems will be taking place on the Earth. I'm not sure that I mentioned units before. Forces. So SI units of mass are kilograms, not grams, kilograms. If you need help remembering those prefixes, what kilo means, front page of the test notes at the very bottom has all the prefixes. So you don't need to memorize the prefixes, like kilo or centi for centimeters, that type of thing. But you do need to know how to use them and how to get to SI units. Acceleration, of course, we already know that is in meters per second squared. So a force being mass times acceleration is going to be a kilogram times meters over a second squared. This is the SI unit for force. We also call this a Newton, as in Sir Isaac. So capital N specifically. Lowercase n is reserved to be nano, the prefix nano. So capital N is our units. So we have a set equation for the force of gravity. The other set equation that we will end up using is that for friction. We typically use a lowercase f to represent the force of friction. The generic equation you will see is this symbol called mu. It is a Greek letter. It is called the coefficient of friction. This value varies depending upon what type of friction we're talking about. So kinetic friction, you would see a subscript of K. Kinetic friction is if the object is sliding on the surface. Mu sub S is for static friction, meaning not sliding. It doesn't necessarily mean not moving at all. It just means not sliding. And then mu sub R is called rolling friction. So the tire is rolling on the ground. is allowing our car or our bike, whatever it is that has tires, allowing that to roll as opposed to slide on the ground. In each case, the force of friction can be represented by this coefficient of friction times lowercase n as a symbol, remember, represents a normal force, meaning the force that the surface is exerting on the object, that force being perpendicular to the surface. In any given problem, kinetic friction will be constant as long as the surfaces, so the object's surface in contact with the table, the floor, a wall, whatever it is in contact with, as long as it's the same materials, then that coefficient of friction will stay constant. The normal force, as long as we're not changing directions at all, will stay constant. So the force of kinetic friction is constant. Static friction, when we say mu times n for static friction, this is only a maximum possible value. I will go into that more after some examples. The rolling friction, similar to kinetic friction, we consider constant as long as the tires continually roll on the same material, same surface. So the coefficients of friction are constants. That depends upon the materials that are in contact with each other. They do not have units. They're just a number. And they are a number between 0 and 1. They can be 1, and in very rare cases could possibly be bigger than 1, but we're not going to talk about situations like that. So as you solve for problems, if you're solving for coefficient of friction, your answer should end up with no units associated with it, and it should end up being somewhere between 0 and 1 in terms of checking your answers. All right, so as we look at problems, we're going to identify forces so that we can draw the free body diagram. That free body diagram, as a reminder, represents all the forces. So we draw all the vectors representing the forces acting on the object. We label those forces so we know what they represent. As a reminder as well, all forces are either contact, meaning they're coming from something in contact with the object we are interested in, or they're field forces, our main example being the force of gravity. So identifying the forces, drawing the free body diagram, then we can write out F equals ma, the net force, Newton's second law. We'll write that out symbolically, and then given the information given in the problem, we can solve for whatever we're asked for. One other thing is there will be situations where the kinematic equations from the last section, we labeled these also the big three, where those will be applicable. So keep in mind, the forces are directly related to the acceleration. If you want to incorporate velocity or time or distance, that's going to be with the kinematic equations. Technically, if we have the varying forces, the acceleration will vary, which means we would need the calculus relationships between position, velocity, acceleration. I don't really give you problems to solve too much with that because simply this is new and can be challenging to begin with anyway. So keep in mind kinematic equations if you are given velocity or distance or time or asked for that. All right, so I'll go through a number of examples, so please go through those and watch for this common problem-solving technique. That's the most important thing to do here. Don't try to memorize final answers, final solutions, final equations. Take the time to understand the approach to problems and solving the problems.